In today's tutorial, we're going to be learning how to do correlation and regression in SPSS. We'll be working from the countries data set. What we're going to be looking at today is a particular variable called the Gini index, G-I-N-I. The Gini index is a measure of income inequality or wealth inequality in a country or any other geographical area. And the Gini index ranges from about 20 on the low end to roughly 60 on the high end. Its mean is around 40. And what it indicates is how unequal the distribution of wealth is. So higher scores mean more inequality, lower scores mean more equality. And what we might be interested to look at, first of all, is whether education has any relationship to inequality. Are countries that have a higher education level more equal than countries that have lower education rates? And we can use the literacy rate as a pretty good measure of education across countries. Well, one way we can do this is to look at the correlation coefficient between the Gini index and the literacy rate. We can do that by going to Analyze, down to Correlate, and choosing Bivariate from the menu. Sort our variables by name and alphabetically. And we'll go and find first the variable we're interested in explaining, Gini, and put in the literacy variable, which is literacy. There it is. And all the other settings are fine. So all you have to do is enter the variables you want and go ahead down to OK. And it'll produce this correlation matrix. Now you can see that it lists all of the variables as columns, it lists all the variables as rows, so it ends up correlating variables with itself, and you can see that produces a correlation of 1. And then off this axis here, you can see the correlation we're interested in, which is between the Gini index and the literacy rate, which produces a correlation of negative 0.263. This other information, the significance, we'll worry about that later when we talk about statistical significance. The n is the number of cases that are included in that particular correlation. Now you see that in a correlation matrix like this, it's kind of a mirror image of each other along the axis because it's each variable being correlated with the other. So you have kind of duplicate information. Now the correlation, of course, tells you the strength of the relationship. The bigger it is in an absolute value sense, the stronger the relationship is. The closer to 0, the weaker it is. The sign, negative, positive, shows you the direction. So this is negative, which means that as the literacy rate goes up, the Gini index goes down. So that means more literate populations have higher equality. And then as literacy rate goes down, we get higher inequality. That's the negative relationship. Now, one of the things about the correlation command is that it allows you to add as many variables as you'd like. So we might add a couple more here that we think have some influence on income inequality. We might, for instance, think that the percentage of the population engaged in agriculture correlates with inequality. Similarly, the urban population, percentage living in urban areas, perhaps has something to do with it. We might also look at the voting age voting age population, or voting as a let's show how this is defined. The average voter turnout during the 1990s, the percentage of the voting age population that voted. So do political factors have some influence on inequality? We can add all these variables together, and what the correlation command will do is correlate each with the other and produce a big matrix, which looks like this. Again, you can see down the diagonal, there's every variable correlated with itself, and the information in this half of the table is just a mirror image flipped over of this information. One of the ways that I like to construct my correlations is to put the thing that I'm interested in as a dependent variable first in the list, so it produces the first column, and then I can just simply read down this column looking at the relationship between my dependent variable and other independent variables I might be interested in looking at. And so you can see here that this is a negative relationship with literacy. There's a positive relationship with the agricultural population, negative with urban population, and negative with voter turnout. And you can see here from this output that the strongest relationship between any of these variables in the Gini index is the voter turnout variable. So it looks like a political variable here has a stronger impact than any of the others. Now, when we talked about correlation regression in class, we talked about the scatter plot as really being the fundamental way to think about interval level variables and the way that they're related. And SPSS has a nice feature to allow you to build scatter plots. And I want to show you how to do that now. What you want to do is go to the graphs command. Skip the chart builder. It's supposed to be a better way of building charts, but it is actually far too complicated and difficult to use. And so what you really want to do is go down to the legacy dialogues, which provides sort of the old school way of doing it, which is actually much simpler. Go down and choose the scatter /dot. Choose the simple scatter plot, and then hit define. Now you see it gives you a choice for your y-axis, gives you a choice for your x-axis. Let's sort these the way we want them. Okay, now remember your x-axis is going to represent your independent variable, which in this case is going to be the literacy rate. So put that there. And the x-axis is going to be your dependent variable, which is the Gini index. Now, one thing I'll show you here, if you're ever interested in using it, if you're interested in identifying particular cases in your scatter plot, you can put a variable here and it'll label each dot in the scatter plot with something. So for instance, if you have a country name, for instance, like this, you can put that into the label cases by, and then each dot will have the country name by it. That's sometimes helpful if you need to identify particular outliers in a scatter plot. For now, we'll leave that blank though. Once you add your independent and dependent variables, you come down and hit OK. And we can see the scatter plot looks like this. And it's got each of the cases represented by 0. It's got our independent variable along this axis, our dependent variable along this axis, the y-axis. You can edit this chart just like any other graph by double-clicking on it, which brings up the chart editor. Let's make this bigger. Now, this is nice because it allows you, if you double-click on this, to you can edit the way that the axes are labeled, and however you want to do that. But one thing I want to show you that is helpful often with a scatter plot is to superimpose the regression line on it. And to do that, we want to go over here and click on Elements, go down to Fit Line, and choose Linear, which is the default option. Okay, and it'll fit your line, and then you just close this dialog box, and you can see that now the regression line is fit on there. It produces a little r-squared statistic here. If you don't really want that statistic, just select it and delete it. Okay, and then when you close the chart editor, it retains that regression line on there. So sometimes that's useful as well. Okay, let's now look at how to do a regression in SPSS. It's pretty straightforward. We go over to Analyze, we come down to Regression, and we choose Linear. Now if you look just briefly at what else is on this list, you'll see some of the more advanced ways of completing a regression analysis. So for instance, if you don't have a straight line with your data, you can do some curves. If you have a dependent variable that is binary, you can choose binary logistic. If you have a nominal or ordinal independent variable, you can choose some of these other kinds of options. So there's other ways of doing regression, but we're going to stick with the most basic, which is linear. Again, we'll sort our variables so we can find what we're looking for. We take our Gini score here and put that in our dependent block. Our literacy rate goes in our independent block. And that's it. Everything else is fine in its default setting. Pretty straightforward. Now we come and we look at our regression results. Now here's what you get. First of all, you have this first block, the variables entered and removed. It tells you what variables were put into as independent variables, and then it tells you what your dependent variable is. And it tells you your method, and there are other methods we're not going to use, but the default one is enter, and that's fine. The next is a model summary box. This will tell you, first of all, capital R. What is capital R? Well, that's actually known as the multiple R, and it's really just the absolute value of Pearson's R. So if we were to scroll back up and look at our correlation matrix, we can see the Gini index in literacy, it has a correlation of negative 0.263, and when we run our regression, we get the absolute value of that in the multiple R setting, which is positive 0.263. And the reason why it's called multiple R is that you can use, as we'll see in a few weeks, more than one independent variable, and it captures the combined effect of all of those relationships. Then, of course, you have R square, which is the goodness of fit for the variable relationship. It shows you how well the regression line fits the data, or how much error there is between the scatter dots and the line. Adjusted R square is a statistic that is sometimes used, especially with larger regression models where you have a lot of independent variables. But for our purposes, we don't need to worry about adjusted R square. We'll just focus on the plain regular R square here. The next box in the output is the ANOVA box. Right now we're not going to do much with this, but it does show you, as we talked about in class, the sum of squared errors as you calculate R squared. It uses this is the sum of squared distances, and for the regular error, and then using the independent variable. And so it's actually these sum of squares here that are used to calculate the best fit, and also to calculate R square. They're also used to calculate an F statistic for statistical significance, which is something that we'll be talking about in a couple of weeks. For now, no need to worry about the ANOVA box. The real important box in regression output is the coefficients box. What it does is it lists on each row the different variables. You have a constant, and that actually is the y-intercept, or the A, in the regression equation. Then you have your variable that you're interested in here, literacy, and then it has an unstandardized coefficient, and that's the regression coefficient. That is the slope variable, or the slope coefficient, I should say. The rest of this you don't really need to worry about. This is the standard error for the slope coefficient. There's a standardized coefficient of beta weight, which we'll talk more about when we get into multivariate regression. And then this T in significance, again, deals with statistical significance, and we'll talk more about that in a couple of weeks. What you really want to take away from this box is two things. One is this number right here, 48.424, which is the constant, and then the slope, which is negative 0.112. Now remember, the slope here tells you the change in y, the Gini index, associated with a unit change in x, the literacy rate. So what this tells you is that as the literacy rate goes up 1 unit, which is a percentage point, the Gini index goes down 0.112. So not a very strong effect. You'd have to go up almost 10% in the literacy rate to move the Gini index down by 1 point. Now we can also take the information in this box and recreate the formula for the line, for that regression line that we have right here. And to do that, we'll bounce over here to Microsoft Word. Remember, the formula for the slope of the line is y equals a plus bx. A is the constant in that formula, 48.424, right? That's going to tell you if the slope is where does this hit when y is 0? Okay, when you're at the axis, the x-axis. How should I say this again? When x is 0, right? That tells you when you're crossing the y-axis. When x is 0, this term goes to 0 because it's 0 multiplied by whatever b is, and that leaves a, and that's your constant. So that's your intercept. Then your slope here is b for your independent variable, so it's negative 0.112. And you can plug this into the regression equation, y equals a plus bx, like this. Right? Y equals 48.424, that's your y-intercept, plus your slope, negative 0.112, multiplied by x. And once you do that, once you draw that information, these two things out of this regression output, you now have the formula for the slope of that line. And it contains information about the slope, which is really what you're interested in here, is the effect size. But it also allows you to create expected values. So you could say, well, what would be the expected Gini index for a country that has a literacy rate of 40%? Well, you can calculate that by simply plugging 40 in for x here and solving this right hand of the equation. It will give you the expected value for that country in terms of their Gini index. Another way to say it is it will give you the value for that particular value of literacy rate it will give you the value on the regression line that corresponds with that on the Gini index. And that's how you do correlation and regression analysis in SPSS.